Hello everybody. I hope you guys are doing well today. So this is the second day of reverse engineering, and today's main focus will be to see how to solve a crack mean. So crack means basically, in the case of CTFs, most of the challenges that you can get for a reverse engineering is something called a crack mean, which is basically like a license check of sorts. You give it some sort of input, and it will provide and it will check whether the input is right or not. So, in the case now, currently, I have this graphic called Chan1. Let's start with the basic analysis. So, whenever you come across a challenge in the case of CTIPs, these are the few steps that a normal reverse engineer would do. First, to see what this is our challenge that we are focusing, the cracking that we are focusing on today. And when I see, first of all, I want to see what the file type is. This can give you a lot of data. Usually, it will be an ELF. But in other cases, when we can easily realize that this is a different sort of file, and we can proceed according to that. Currently, it's an ELF. Now I can do something like strings, which will print out the strings or the printable text in a particular tab in this particular file. You see a lot of stuff. You see main, and you can see enter your answer, you win and you lose. Now these are this is a small form of like starting analysis that you can do with the file. Or to run a file, you have first you have to chmod it, which is giving its permissions, but after that you can run this file. So currently this file is asking for some input, some sort of input. Let's put some hello or something, and it's saying you are posting. Now we can try something different. 15. Okay. It says now for a reverse engineer, we have a certain set of tools that we can use. Last session, you guys might have heard about something like GDB or IDA or GitHub or tools like that. So these are called GDP is what we'll be focusing on right now. It's a very useful tool that you for reverse engineering to use that onto a file. We can use something like this. Okay, this is how you start GDB. Now, this what I'm currently using is not just normal GDB. I'm using another plugin for it called Jeff, which is enhanced features for GDB. It gives a lot more functions. You guys can are free to try out all the different plugins if you come across some of it. Yes. So let us start with how to reverse a track. So first, what I'm going to do is I'm going to how to run the program. Okay. First, we start with that. We can do R, which will run the program normally. Now, it's asking for us to give an answer. I'm giving 40. It's exited, as you can see. Now, let us see how to what we say properly debug. For certain files, you can first of all for this file we can particularly see that it's when I did file it says not strict. So not strict is a very good what do you say induction, like a very good stuff that you can see for a crackling. So it basically means that you have a lot of your functions named even if you're disassembled. So, so after doing that, I'm doing. Uh, you know that in all the C files start from the main function, right? So we are going to break. A breakpoint is something which can prevent the execution of particular file when put into a debugger. So basically, when I see a particular address where a current instruction is, I can put a breakpoint at that instruction. So when the program is executing each instruction one by one, and when I reach that particular instruction, it will stop executing. So let us do that. When I do break main, what it does is that we have the main function, right? So whenever the program execution reaches the main function, it will stop there. So I'm going to do break main, and then I'm going to run it. So when I run that, we can see this. Yeah, I'll have to show you. These are all the registers that we have. This is the stack, and these are the current instructions that we need to that we are executing. Now, RSP, this is stack pointer. and RPP is the base pointer. Now I'll be showing, first of all, when you do sub RSP 0x20, basically what I'm doing is that I have, suppose this is how the stack looks. Okay, I am having my base pointer over here. So the thing to note is that the base pointer will always be at a higher address. All the pointers, like this is the stack pointer, this is the base pointer. So I am going to put RBP over here, uh, R plus P over here. So this is the base pointer and this is the stack pointer. Now when you do sub RSP 0x20, first of all, what is happening here is that both RSP and RBP are being at the same address. So when I'm subtracting it by 20, what happens is that now the RSP is here. It gets since we're subtracting, this will have a higher address. So higher address, and this will have a lower address. Okay, now we are seeing sub RSP 0x20. So basically, from the value where this is pointing to, we'll come across, we'll discuss about a pointer also. So basically, a pointer is kind of like a box. Okay? Suppose this is the box that I have. Pointer is basically I am putting some data into this box is now a memory address. And at that memory address, I am putting this data there. Now, what a pointer can do is that when I, this is the pointer. Now, we have this pointer. So when I do something like dereference, what do you mean by dereferencing a pointer? Is what we get. When I, this box is, wait, where is it? First of all, let's just think that this box is covered for now. Now, when I just directly take a pointer, what we can see is this box, which is the memory address. Now, when I say that, I need to see what is inside the box. That is known as dereferencing. What happens is that I can now currently see the value inside the box. That is called as dereferencing a particular pointer. Now, this RPP normally has a memory address that it contains. Now I'm subtracting 0x20 from that memory address. And now that is, look, since RGB and RSP are pointing to the same address, when I'm subtracting 20 from RSP, what happens is that this moves still here. And the size of this current stack will be 0x20. Okay, this is how many bytes there is. Now, these instructions, we will not be looking in the current, what is it, what the use of these instruction will not be, it's not in the scope of this current session. We'll look that in the upcoming days. So this is where we start from. So one thing to note is that all the local variables of a current function will be stored inside this inside its own stack file, and all the global variables will be stored in a different section. So local variables are for this current thing. And first, before that, let's see. We see the keyword BTR RPP minus 0x8 RX. Keyword, if you have looked at the session, yesterday's session, we know that it's 16 bits, which will be 64 bits, my bad, sorry. Okay. So we'll, this is the RDT, and from RDT we are taking this much space. Okay, so this will be 8 bytes will be allocated for this. So from the rest, what, how much do we have? We have 20, 0x20 minus 0x8 bytes. So 0x20 minus 0x8. So we have a number of 24 bytes remaining from this location to the stack pointer. Now we are seeing that, and also show how the stack is viewed in this GDB. So I'll also print these. P is for printing, and X is what I told about dereferencing, right? So X is for dereferencing a particular pointer. So you see that this is at address DAA0. Now, and also renders RSP. So, as I told before, the RSP is at a lower address than the RPP. Now you can see that D80, you see D90, but you don't see DA0. So, in how this is being arranged is that, see, these are each of these sections, okay? These are 8 bytes long. So, put a keyword, okay? So, this 80 is being pointed to by this address. So this is 80. Uh, okay, this is 889098. See, each of these places when it points to is are 8 bytes in difference. So when I look at this particular what is it keyword, this will be at the memory location DA80. This will be at the location DA88. This is I should show. Okay. If you've seen that at D888 location, it is pointing to here. Now let's see what the byte is also. So 88 is currently pointing to this byte. 89 is here. So 8A will be here. Since it's X, we are not knowing that X. So it's going like this. Now let's look at 80. 80 is now pointing to here. So it's not starting from here. You guys have to take in consideration of little endian and big endian. So this will be 80. I mean, this will be 8081, like that. See, 8081, like that it will go. Similarly, in these one. Now, wow, that yes, here we are seeing MOV dword PTR RPP minus 0x18 0x8. Okay, so basically we have told that for a stack we have push and pop functions, okay? But even if we push and pop, we can still access the memory locations that are inside the stack. So what I'm currently doing is that from RPP, that is from this location, I am subtracting 0x minus 8. So I'll get some value, right? So at that value, I am putting the value 0xa. So let us see that. So we need RPP. So RPP minus 0x 18. So we get this address. Now currently this instruction has not been executed. Now let's see how the stack looks after the instruction is executed. You might be a little bit too rich. This is what we need in the connection. So if you've seen that, we are moving MOV. MOV basically moves this value into this memory location for this current instruction. So now I'm moving 0x8 RPP minus 0x18. Okay. So what do you get as 0x1 RPP minus 0x18? That is this memory address. So when I do uh, X is dereferencing yet again. This is a memory address, not a value inside the memory address. So to do this address, we can see that. Wait, my God, field change. Okay. At that current memory address, we have put in the value 0x8. Now, another thing to note is the D word. So D word is basically is 4 bytes. So one such, what is it, in data type. Data types are basically a different types of what is it, data that we kindly declare for different variables. For example, for a is equal to 5, I get if in C, what we do is that int a is equal to 5. showing that it is an integer number. So currently we have put 0xa into a D word. So that is 4 bytes. 1, 2, 3, 4. So this is what is being allocated for putting this value 0xa. Okay, these 4 bytes are for this. Now let us look at the next instruction, which is move D word ptr rpp minus 0x1 for 14. So I shall be dividing this into few blocks. And come to that, and I probably explain it. Now, at this position, this is the stack pointer, okay, at 80. So this will be 80. This current 8, this is at 8 bytes. Now this is 4 bytes which is being allocated for it. We have seen 8 is the starting here, okay. So 8 9 8 8 9 8 it will go like that till 8f because plus 8. So and it's in hex. So, yes. Now coming to the next instruction, which is move dword ptr rpp minus 0x14 0x14. So basically, I am moving the value 0x14 into the memory location that is being pointed by this guy rpp minus 0x14. So let us check what rpp minus 0x14 is. Minus 0x14. You see that this is pointing to DAHC. We just need to worry about the last, what is it, 4 characters of the 2 bytes because the rest of them is pretty much the same. For DA8C, where might that be? Let's see after we execute this instruction. We are going to again execute this instruction. You see this from the previous thing where the value was this 0000 and 08. We have 0x14 over here. Now this is also another keyword, so which could mean that this is also another integer. So this is one keyword, this is another keyword, and this is the top. This points to the top of the stack. Now the third instruction is also pretty much the same, but now it's only at 0x10. Now let us just execute that instruction also. Now let us see what is in the stack, right? But what do you know? The 05 is here, which is also a debug. Okay. All right. Now, now these are basically what do you say, local variables, and they are being initialized with some value, and that values are in the stack. Okay. As we told before, that local variables will be there in the stack. Now let us see what the next instruction will be do. So from here, keyword ptr rpp minus 0x18. Now if you have seen here, we saw that rpp minus 0x18 has the value 0xa. So now currently what I'm doing is that from rpp minus 0x18, I am copying the value and then I'm placing it into edx. Okay, edx is another register. The size of edx is half of that of rx, which is 32 bits. So 4 bytes. Now, when I see the value of RDX, oh wait, my bad, RDX is the bigger one. So, which is the 64-bit version of this register EDX. So now the value 0xa is moved into RDX. So I'll be writing that here. RDX contains a value 0xa. Now let us see. Now this EDX, no? So that EDX, now I'll give you a small visualization on how it works. This is the register, okay? Suppose this is the register. This entire thing would be RTX. And just this part will be the EDX. So this will now this part will contain 0x a. But even when I'm referencing to see what the value of RTX is, that is since this is a smaller part of our RTX, this will also contain 0x a. It's basically like building blocks. So if we seen that the value of EDX is being put now 0xa and EDX. Now what's the next instruction? MOV EAX EDX. EAX is also the third two bit form of the register RAX. Okay. Now I'm going to move the value from EDX to EAX. So what it does is that from this register, okay, this part EDX, I'm going to move the value into EAX. Now when I say the instruction move, it's not essentially completely moving the value from 0x8 to 0x. I mean, like moving the value from one register to another. What it does is that it copies. It copies. It does not totally move from one place to another. It copies from this particular location and puts it into this guy. So when I do MOV EAX EDX, what happens is that since 0x A is an EDX. This is being copied and placed in EAX. So now both EDX as well as EAX contains the value 0x8. Okay. Now, so let's just see. Currently, RAX, which is the smaller part of, I mean, which is the bigger part of EAX, has 0, and RDX has the value 0x8. Now, let's see what happens when I move it to it. Now, when I move the value, you see that Rx now also has 0xa, RTX also has 0xa. Now, both of these guys have 0xa. Now, next is another interesting instruction. We have something called SHL-EA0x2. SHL stands for shift left. So basically, the idea of that is that we shift one bit for all the bits. Now, I that might be a little bit hard to understand. So I'll just show you what SHL EX0X2 means. So we have the instruction SHL X0X2. Now, currently, what is the value inside EX? EX had the value 0x A. Now, what is A and X is basically 10. Okay. So it will be 0, 1, 0, 1. Okay. Now we have a lot of, what is it? Zeros preceding it. Okay, that will be that. Oh wait, no, this is what 0x is because this is the first bit. This is which can have values 0 and 1. This is 2. This is 4, and this is 8. So how do you convert from bits to normal numbers? So basically, you just do 0 times 2 raised to 0 plus 1, since at this location it's 1, 1 times 2 raised to 1 plus 0 times 2 raised to 0 plus 1 times 2, oh wait, my god, not 2 raised to 0, 2 raised to 2 and 2 raised to 3. Okay, now what is the value of 0 x 2 raised to 0 will be 0, 0 plus 1 times 2 raised to 1. What is that? 2 plus this is again 0 plus 2 cube. Or what is 1 times 2 raised to 3? So 2 raised to 2 is 4. 2 times 2 times 2. So this will be 8. Now the total sum of this will be 10. So this is the binary representation of the number 10. Now when I do shift left, what happens is that I shift all the bits to the left side once. So this is going to be like 0, 0, 1, 0, 1, 0. This is how we have harmony. Now we are shifting all of these guys one place. Okay. When I do shift left by 1, essentially, it's 1. So when I do that, what happens is that the number is currently 0, 1, 0, 1, 0, and another 0, because we are moving the entire thing to one place. Okay, now what might this be? Now currently when I take the number of this, it would be uh, 0 times 2 raised to 0 plus 0 times 2 raised to 1 plus 1 times 2 raised to hmm, plus 1 times 2 raised to 3 plus 1 times 2 raised to 4. So what will this be? This is 0, again 0. What is 2 raised to 2? 2 into 2, 4. Now this is supposed to be 0 like that. So 4 plus 0 plus what is 1 times 2 raised to 4? That will be 2 into 2 into 2 into 2. So 8 times 2, that will be 16. So this value is currently now 20. Okay, that is only after you shifted by once. Now when I shift again, what will the value be? The binary will now look like 0, 1. Oh, no, wait, 1, 0, 1, 0. So this thing is being moved here. 0, 0, 0. Okay. Now let's just convert this to a number. So this will be 0, 0 times 2 raised to 0, 0 times 2 raised to 1, 0 times 2 raised to 2, 0 times 2 raised to 2, 0 times 2 raised to 4. That is 16. I mean 1 times 2 raised to 4. 1 times 2 raised to 4, which is 16. Okay. Then 0 times 2 raised to 5, which is 0 times 32. That will be another 0. And then this will be 1 times 2 raised to 6, which will be 64. Okay. So this will be 16 plus 64. Sorry, I made a mistake. Player removing. So that will be 1, 0, 0, 6, 7, 2 is 1, 2 is 2, 2 is 3, 2 is 4, 2 is 5, and 2 is 6. That is 0 times 2 is 0. Yes. 0 times 2 raised to 1 plus 0 times 2 raised to 2 plus 0 times 2 raised to 3. 1, 2, 3, 4. 1 times 2 raised to 4 plus 0 times 2 raised to 5 plus 1 times 2 raised to 6. 2 raised to 3 is 8, which will times 0. 1 plus times 2 is 16. Now 16 plus this is 0. I mean, not totally 0. This is 0. Plus this 2 raised to 6 is 64. Split this. Let us see. Oh, wait, my bad. I made it. This, I'm not supposed to have 1, 0, okay? I think I'll have to explain this again. Right. Yeah, I'm only have supposed to have. I added another 0. So it should be 1, 0, 1, 0. Yeah, this is what we are supposed to have. I added another 0 here by mistake. So just clearly so. No, this will be 0 times 2 raised to 0. I hope you guys get the calculation that's happening. This is 2 raised to 0, 2 raised to 1, 2 raised to 2. This is 2 raised to 3. So 1 times 2 raised to 3, okay? Plus uh, 0 times 2 raised to 4 plus 1 times 2 raised to 5. Okay, this is what you're supposed to do. So this is 8 2 raised to 3, 1 times 2 raised to 3, and this is 32. Okay, now you add both of them. What is that? 8 plus 32, you get 40. So now, when I had EAX as 10, now when I shifted it by 1, SHL EAX 1, we got 20. Now when I shifted it by 2, got 40. So I hope you guys are seeing a pattern here. So 10 times 2, again times. So each time when I shift once, basically my number in mathematical sense, what happens is that I'm just multiplying it by 2. Now let us look here. When I do SHL EAX0x2, what will happen is that the current value of EAX, which is 0xa, it is going to be shifted into 2 into 2, which is 2 raised to 2 times. Okay, 2 raised to 2 times. So basically, enter shifting process number into 2 raised to number of times you are shifting. So I'm shifting it by 2 times. So 0xa into 2 into 2, which will be 40. Now let's see what's the value of EAX after this instruction. It is 0x28. Okay, let's see what that is. Okay, we see that it's 40. Alright. Now, what we EAX now contains 40. Now what they're doing is that add, and they're storing the result in EAX itself. Okay. Now the next instruction is add EX and EX again. So what is the value of EX? That is 40. And then adding 40 with 40 and then storing the result in EX itself. That will be 0x28 plus 0x28, 18. X of that is 0x50. Now let's see if that is correct or not. Uh, Wait, my bad. We missed an instruction. So add EX, EDX. What is the value of EDX? EDX had the 0x that was previously saved. Okay. Now that is being added to 0x28. So 0x28 plus 8. Oh, my plus 8, my bad. 0x28 plus 0x8. 50. You take the hex of that. That is 0x32. Let's see if that's correct. See, the value of Rx is now 0x32. Now what they're doing is that they're adding EAX with EAX and storing the result in EAX itself. That will be 0x32 plus 0x32. Okay, that is 0x64. So basically, now the value of EAX after this instruction should be 0x64. Let's see if it's correct. See, you see that the value of Rx is now 0x64. Now, what is happening here? Move EAX, and they're now moving the value of EDX or EAX into EDX. So basically 0x64 will now be copied from this EAX register and be put into our EDX register. Let's just execute that. Now you can see that both are RTX and RTX will now 0x64. Now let's see what this is basically dereferencing a particular memory location, which is RPP minus 0x14. Okay. Now let's see what is that? RPP minus 0x14. Oh, we already have a value. So exceptions. When I do this, we are basically having 0x14 at this particular memory location. Now, what I'm doing is that I'm dereferencing this memory location, taking the value of this and putting that into EX. Okay. So at the end, the value of EX should be 0x14. Now let's see if that's correct. See, the value of RX is now 0x14. Now what they're doing? They're adding the value of EAX with the value of EDX and storing the result in EAX itself. Now, what's the value of RTX, which is basically the bigger form of EDX, as I said before? 0x64. That is being added with 0x14. Okay. So 0x64 plus 0x14. That is 120. Okay. That's 620. That is 0x78. All right. Now, basically, I after this addition, what happens is that the value of EX should be 0x7. Let's see if that's correct or not. See, the value of RX is now 0x7. Now, what are they doing? What they're doing is that they are doing sub, which is basically subtract. Okay, they're subtracting the value of EAX with the value of RBB minus 0x10. Now, what did RBB minus 0x10 have? We, DA minus, let's see. That is this value. Okay. So this we already saw that it's a D word. It will be this these 4 bytes. So which is 5. Now I'm subtracting the value of 0x78 with the value 0x5, and I'm putting the result in RH itself. Now let's see what that is. 0x78 minus 0x5. So that will be 115. Take the hex of that. That will be 0x73. Let's see if that's correct or not. As you can see, this value is now 0x73. Now, I am putting that value into this memory location. Now, let's see the stat. Okay, this is in the stat still. So let's see the. This is before this instruction is being executed. Now let's see how it looks after the instruction is being executed. Okay, we see this. Okay, so basically an integer or possibly a D word with the value 0x73 is put into this location. So that is the result of all these operations. What is this? RX. We are moving, loading the address, some address, okay, of which is pointed by this into RAX. Now let's see what this RAP plus 0x E0B is. Now, slash GX. Hmm. I think I understand this properly. So let's try a different data type, maybe a different form rather than X. Different. Wait, let this instruction just be executed. Okay. So it's easier for me to get. So now this address is now taken and it's put into RAX. Okay, the address is LEA basically means loading an address, effective address from this memory location into this register. Okay, it's not dereferencing at that point. It's just loading. That means just taking that address and just placing it there. Copy of what the address location is and placing it in RAX. Now let's see what RAX contain can. These efforts. Okay. Now this is what the value of RAX is. Now, let's measure this dollars. Okay, what is this? We see a lot of hex values, but if you look at it closely, 456E74. These look like printable ASCII values. Okay, so if you don't know what ASCII values is, those are basically numerical representation of actual English alphabets or numbers or special characters and stuff like that into a binary form or a number form, such that it's easier for the CPU to understand. Now, inside GKP, you can basically print out strings. Okay, so for that you just use S here, and when I do this, we can see that that memory location contains the string, which is enter your answer. Now, if you guys remember, should see this was what it was prompting. Okay, so this is what is being put into RDA. Now, when I do here, EX is basically being cleaned out, and I am calling a particular function. Now, what is this function called? Point to printf. If you guys have dealt with C, worked with C, you know that printf is basically like print, but for C. So what is this doing? Basically, whenever you call a function, you guys have probably came across functions in Python where some functions will have stuff called arguments. Okay, arguments are basically parameters that you pass into the function. Now, what inside C, inside assembly, there's something called a calling convention, which is basically the order in which what all registers you have to fill, so that when you call a function, that those will be used as arguments for that function. Now, in the case of x86 assembly, we have these registers called which will be RTL and RTI RSI. There are a lot more registers, but we are currently not going to look into that. You guys can also look into calling conventions. Calling conventions in x86. I'm just going 64. Okay, this is what you guys have to Google. All right, without the arrow, of course, and you guys will see what I'm talking about. So basically, for this print function, I am passing the argument which is RDA. What did RDA have? The value of RX was being moved into RDA. So what did RX have? RX had the, what do you say, the address that pointed to this particular string. Enter your answer. Okay. Now, basically, what is doing is that I am calling the function printf with this argument. Now, let's see after I print. Okay, you can't see it here, but basically, what happens is that I basically printed. We are executing instruction by instruction. Okay, so I just basically executed this one, just this part. Okay, that's what happened. Now, again, we see LA RX R2C minus 0x 1C. So basically, the address 0x1C is being put into RX. LA is basically just loading the address. You don't want to do anything else. So RX will now contain this address. If you guys remember, let me just show the address again. Okay. If you guys see, this is the address, and that is pointing to this guy. Now, it's basically this and this part. Uh, it's fine if you guys don't understand this currently. We'll look into it later. Okay, that's fair. So just know that I am basically just loading this address. I mean, taking this address, what is being pointed to by here, and I'm putting in this register. Now, what I'm doing is I am taking the value, this address, and then putting it in RSI. If you remember, if you can look at it forward, you see another call function. So as I said before, RTI, RSI are registers that you can use for parameters for the function. So we can guess that this address is possibly a parameter for this, what do you say, a parameter for this function call. Now let's see. RIP plus 0x E4. What might this be? Let's see. X. Hmm. Let's see. 722075. It's very suspicious. So I'm just going print it out as string. So you guys see quotes percentage again, percentage D. Now, in the case of C, how you take input is that you can have something called format specifiers. So This is basically how it looks like. Scanf. This is the function that we have here. Okay, scanf, just like in Python, how we have input. The scanf is basically just taking input, but in the case of C. So you use something like percentage %d, comma, and then address of some variable. Now you see here, you remember for the two parameters. The first parameter will be RD. Okay, RD contains this guy, which is percentage %d. What did RSA contain? RSA contains a location, as a particular memory location. So we can guess that that memory location, or it is that memory location is for another variable. Okay, so let us see what happens. Yeah, it's calling this one. Then I press enter. You guys can see enter your answer, and then it's waiting for some particular input. We are asked to give an input again. The execution is not happening right now because it's waiting. The program is waiting for an input. And we have calculated all of this, okay, and we got that the final result was 150. And let's see what happens if I give that as input. Give that as input. Okay. Now we saw this particular memory address, right? Okay, like I told you, this will be a memory address. Now that was 0x1c. Let's see what's in 0x1c. See, that is the input that we gave. I'll show you again with when we give a different type of input. Okay. So now this value 0x, I am moving and I'm dereferencing that particular memory address. So basically, I am moving the value inside that address, a D word value, that is 4 bytes of value from that memory address into the register EAX. Now let's see what's the value of EAX. EX is now 0x73. That is whatever input that we give. Okay. Now, now basically it's CMP. Now how does CMP? CMP is basically compare operation. Now how does this work? This is the first operand and this is the second operand. What it does is that if you guys have attended yesterday's session, you guys will know that these are called operands. So operand 1 minus operand 2. Okay. When I do subtraction, it's a very good way to compare. Okay, if you guys have remembered something, we probably discussed about something called as flags register. So flags register contains a lot of stuff like sign flag, zero flag, and currently zero flag is what we need to care about. So zero flag is a what do you say, 1 bit that is being set when any particular operation yields the results or gives out the results zero. Now, when I compare two numbers, if they are equal, if I am comparing 5 with 5, what happens when we subtract both of them? We will get the value 0. So when I get the value 0, what happens is that this 0 flag will get set. So that means saying that if this particular operation gave the result 0. So the 0 flag will now be set to the bit 1, which means that a particular operation gave the result 0. Okay, so basically 0, it's comparing RPP minus 0xe, which we saw was 0x73. Wait, that was okay. This is 0x73. Now what's the value of EX? EX was also 0x73. So both of them are the same. So what happens when you subtract both of them? When you subtract both of them, what happens is that the 0 flag will be set. Now let's also look at another instruction, which is JNE. So jump not equal to. So when I told you guys that when it is equal, both of them will give the result 0. So the 0 flag will be set. So what happens when it's not equal? When it's not equal, what happens is that this 0 flag will not be set. Okay. So the program is like, okay, these guys are not equal. So basically what JNE means is that jump not equal. So jump if so basically if this compare statement or this compare instruction After comparing, if both of these guys are not equal, I will jump to this particular address. Okay, this particular instructions address. So let's just check what that is. I is for instruction. See, these were all the different values. Now, in our case, both of these are equal. Okay. So what happens here? The zero flag is set because both of them are equal. So now computer knows that this we don't need to take that. Why? Because the zero flag is equal. That means both of these values are equal. So we don't need to jump here. Let's just continue executing from here. Now when I go here, we see another RIP plus 0xDE. Let's see what this is. Okay. Let's just take it from RAX itself. That value is being moved into RAX. Now, if you look at the RAX, you see that RAX contains this address, which is pointing to the string you win. So basically, what happened to this program was we had all of those values that were initialized before, and after a lot of operations, arithmetic operations on it, the final result is being compared to whatever input that we were giving to. Now, what happened is that okay, so basically now this RAX is being moved into RDA. So you guys know what? Okay, I've told about the calling convention now. So this will be the first argument. I put this as a null. So these are the arguments that are being passed to us. So RDA now contains the value you will contain the address to the string you pin. Okay, I am executing this. I don't see. If you look here, it has printed out the string you pin. Okay. Now what happens after that is JMP. What is JMP? JMP is like jump to this particular location. The other cases also we had jump, but those are called conditional jumps because you have to satisfy certain conditions for it to jump. Now this jump is called an unconditional jump. So when we have this instruction, what it means is that it will anyways jump to that particular location. So now what happens is that this instruction will get executed and 55249. Where is 249 here? See, 24. Okay, so basically this instruction will not execute these three instructions and will go here. Now we also want to see what these three instructions are, right? So here is it was 0xd to b. Let's just see what's the address. Uh, oh wait, my bad. Anyways, I think I'll come to that off by executing. It'll be easier to see. Okay. Anyways, now see this part was not executed. We are now here. Oh, these stuff, I think it will be covered in later chapters. I mean, later sessions. We don't need to worry about that now. Okay. Now we have returned. Now we saw that what we needed to give for the challenge was the number 115. Let's see if that's correct. See, you have gotten you bit like this. See. Now, what I'm going to do is I'm going to run this program again just so we can see what's the second part of the you lose part. Okay. Now I am making it again, running the program. Now I just want to go to that particular address. Okay, let us see. We see one puts here. Basically, we wanted to go here, right? We take this address. These I put a breakpoint out there. Breakpoint means that whenever the CPU ever comes across that address which contains an instruction to execute, it will stop executing over there. So I'll be continuing. It's asking for an input. We gave 115, which was the correct input last time. So let's give something like 36 this time. Okay. Now we are at where we put the frame point. Now let's see what's the value of Rx. If you look at Rx, we see that Rx contains this address. Now, what does this address point to? It points to the string you lose. Okay, so if I wait, I've gone a little bit too up. Okay, you guys see that you lose a string. So this is basically how you solve a very beginner or a simple crack. So this is how assembly looks in the case of a simple crack. So I hope you guys have understood what the session was about. If you guys have any doubts related to this session, you guys can send it in the Discord group. Anything as you wish. Okay. So have a nice day. Thank you.